So let's start our discussion on energy bands, and we will see that they are very useful to understand the operation of MOSFET. So here we have the gate, here we have the oxide, and from here to here we have our semiconductor. And then we have several bands. So by bands I mean EC, EI, EF, and EV. So EC is conduction band, EI is intrinsic band, and EF is Fermi band, and EV is valence band. Okay, so as you may have studied that electrons are in different shells, and we have valence shell and we have conduction shell. So we want to understand the operation of PN junctions, and for that matter MOSFETs, using these different kinds of bands. Okay, on the X, on here below we have this X, which denotes the position along the horizontal direction, position along horizontal direction from let's say oxide. Okay, so you see this is the normal situation, and this semiconductor is p-type semiconductor. Why p-type? In a p-type semiconductor, the EF or Fermi level will always be near to the valence band. Okay? So you have to remember this, that in a p-type semiconductor the Fermi level is near valence band. So, and in the n-type it will be near to conduction band. So let's see what happens when we apply a voltage to the gate. Now this is the situation when there is no voltage. What will happen when we apply a voltage? So in order to understand that, we have to see what happens to electrons when we apply a voltage V. So basically it pulls, the voltage V pulls the electron into a potential, you can say well. Okay, it pulls it into a potential well, so it basically lowers the energy of electron. Okay, so because the voltage is positively charged and the electron is negatively charged, a positive potential will lower the energy of electron, and a negative potential will enhance the energy of electron. And the energy of electron in this case is energy is equal to minus charge times applied voltage. Minus because the electron is negatively charged. Okay, so this is what happens when we apply a potential to a electron. Now here is the graph showing what happens with the potential as a function of the position along the x-axis. So near the oxides, the potential is sort of maximum, and it goes down to its minimum value as you move along the semiconductor towards horizontally outside. Okay, so this is what happens when you apply a voltage. The potential is strong near the oxide, and it goes down as we move along the x direction. So this is what happens when we apply a voltage. So in the previous slide we saw that we applied a voltage Vx, and this was our x, and it was something like this, that near the oxide it was greater, and as we move away from the oxide it becomes negligible. So our what happens to our bands is this one, that each of our band is basically proportional to the negative of applied potential. So you see that before the conduction band was here, but now it moves from here to here. It is due to this applied voltage. Similarly, the intrinsic level has moved. So you can see that the EI has bended and EV has bended, except the Fermi level. The Fermi level is constant. Why? Because the current flowing is zero. You only applied a voltage at the gate, but we have so here we have the gate, here we have the silicon dioxide, and then we have here a p-type region. So even if you apply a voltage to this gate, you see you cannot make current flow in the p-type semiconductor because of this insulator. Okay, so the insulator has an effect that it does not allow the current to flow in this kind of structure. So that's why the Fermi level depends on the flow of current, and it is constant. All other energy bands have moved down. Okay, regarding the intrinsic band, it is the middle of EC and EV. So it's the middle of conduction and valence band. Okay. Now there is another formula up here, which is this one. So basically what this tells, Ex is basically the electric field along the x direction, and electric field is the slope at any point. The electric field is the slope of the energy band. Okay, so here we have a positive slope, which means that the electric field Ex is strong here. Okay, and here you see the slope is 0, so the Ex is 0 here. Okay, so electric field is the differential of band along the x direction. Okay. Then we have the number of electrons. N is the number of electrons, and Px is the
number of holes. We have these two formulas here, and we have only to remember that the number of electrons are proportional to the difference of Fermi level and intrinsic level. Okay, so if the Fermi level is above the intrinsic level, the number of electrons will be large. For holes, the formula is like this, that so for holes, the formula is intrinsic level minus the Fermi level. So what this means is that if the Fermi level is below the intrinsic level, the number of holes will be more. Okay, so let's move to the next slide. Here is again the energy band diagram, and what we want to read the energy band diagram. So we already know the first formula from the previous slide, that the potential along the x direction is proportional to the negative of our band. So this is our band. Okay, the electric field E is proportional to this thing, which is the slope of band. Okay, and this is the number of electrons, which is proportional to the difference between Fermi level and intrinsic band, and the number of holes is proportional to the difference between intrinsic band and Fermi level. The last one, so this was let's say 3, and this is also the same formula for holes. And then we have the fourth one, which is this charge density. So how much charge we have per unit area. It is basically the second derivative of our band. So it basically comes from this equation. So in this equation, the charge density rho x is Ks epsilon naught d by dx. Okay, and basically this is our electric field, and if we put the value of electric field from above, so it becomes d square Ecx by dx square. Okay, so this is like constant, and we have this proportionality. So you see here, if I explain it from here, you see that here, for example, on this point, this has bended because of Vx was maximum here. So it pushed EC from here to a lower point. Okay, and I told you the electric field is the gradient or slope. So here the slope is positive, so electric field is strong here. Okay, and here the slope is 0, so electric field is weak or 0. Now look at this point. We have E, this red one is EF, and this is EI. So the Fermi level is above the intrinsic level. So that means that the number of electrons are large here near the insulator. The number of electrons are large, and if you see here, okay, so EI is above EF, which means that the number of holes are larger as we move away from the insulator. So let's consider another example. This example is slightly complicated because we have an N-type semiconductor and a P-type semiconductor, and they are joined. So we have an NP junction. Okay. So on this side, we will have electrons in the N side, and on the P side, we will have the holes. Now, as I told you, that far from the junction, the band will be flat on both sides. So you have already seen the energy band diagram of a P-type material in which the Fermi level was near the valence band. Now, so on this side, the Fermi level is near the conduction band, and on this side this is the valence band, and on the P side it is the Fermi level is near the valence band. So this is the procedure to draw the energy band diagram of the NP junction. The Fermi level will be aligned due to equilibrium. So by equilibrium we means that when you join the N and P region, there will be a transfer of electrons and a transfer of hole across the NP junction, and eventually they will go randomly from one side to another, and eventually an equilibrium situation will be attained. So the Fermi level of the NP junction will be the same, because the Fermi level represents the current. So this is the energy band diagram. On this side we have the N region, and on this side we have the P type region, and you see that these bands are flat. So and note that on the N side the Fermi level is near to the conduction band, and on the P side the Fermi level is near to the valence band. So this is our EV, this is our EF, this is our intrinsic band, and this is our conduction band. So you see that the Fermi level is aligned, and you have this transition region. You see it's like a uphill, a steep uphill drive for electrons. So this is the energy band diagram of a PN junction without any applied voltage. So now we want to read the E band diagram. So what that means is, as I told you before, this is the second example. So the potential is proportional to the negative of band. So you see, if the band here is low, so the Vx will be high. So if this is low, this will be high. Okay, so this is the Vx curve. You see, EC was low here, so it is high, and EC high EC was here, so it is low. And because of this NP junction, you see there is a potential difference. On this side the potential is high, and on this side the potential is low. So this is called VBI, or built-in voltage. Okay, if we want to talk about the electric field, so as we discussed before, the electric field is the differential of band, so it is the slope of band. So the slope here is 0, here we have a positive slope, here we have a 0 slope. Okay, so you see it is like this, it is maximum here because the slope was positive here, and then it goes to 0 and 0 on both sides. And the carrier density is this one. So you see it depends on the difference between Fermi level and intrinsic level. So you see here the Fermi level is above the intrinsic level, and we have a large number of electrons. Okay, and on the other side the Fermi level is below the intrinsic level, and we have in this region large number of holes in the p side. And the charge density is we said that so the charge density, the red curve is showing the number of electrons. So the number of electrons are higher on the n side and low on the p side, and the blue curve represents the number of holes, and it is higher on the p side and lower on n side. Okay, so this is the charge density. And as we talked that the space charge density is the second differential of energy band, okay, or the first differential of electric field. So calculating the second derivative is difficult, so we have an alternative formula, which is this one, that the space charge density is proportional to, this is the number of holes, this is number of electrons. So the space charge density, as we showed, depends on this formula, and Nd is the number of ionized donors, okay, and it is the number of ionized acceptors. So number of holes minus number of electrons plus number of ionized donors, this is number of ionized donors are on the n side, and number of ionized acceptors are on the p side. So when you add up these things, you get the space density. And this is if you add up these things and plot it, the curve will look like here. So this is the space charge density on the n side, and this is the space charge density on the p side, and this is the donor concentration, and this is the acceptor concentration. So you see, if you look at the NP junction, if you remember that there was this depletion region. Okay, so there was this depletion region that is here. Okay, so that's why in the depletion region we only have ionized donors and acceptors. Ionized donors and acceptors. So this is the space charge density. So this completes our discussion about the introduction of energy bands and how we draw energy band, what happens when we apply a potential difference, and how we read the energy band. In the next part, we will apply the energy band concept to understand the operation of MOSFET.